Video, I'm going to solve this problem, acceleration of steam in a nozzle. So you see here, steam at 1.8 MPa and 400 degree centigrade temperature. It is steadily enters a nozzle whose inlet area is this. So look at this cross-sectional view of the nozzle here. This is actually the inlet, this is the outlet. For inlet, we know the pressure, we know the temperature, and we know the area. For outlet, we know the pressure, we know the velocity. So here, if you see, we don't know the temperature T2, and here actually we don't know the the velocity V1. If you look clearly, P1, T1, A1 it is given, so V1 it is unknown. But here actually we know P2, V2, but we don't know T2. What we know, the mass flow rate of the steam. So steam is entering into this nozzle this way and it is exiting this way. So we have one inlet, one outlet, right? In this case, yes. And the heat transfer, you can see it is 2.8 kilojoule per kg. It is going out. So this is this dotted line. We assume this nozzle, it is as a control volume CV. So this is the control volume CV. You can see this dotted line. So the the energy is transferring from the system to the surroundings. It is 2.8, and you see all other conditions are given. So what we need to do is we need to calculate the heat loss. Okay, no, heat loss is given, it is 2.8. So we need to calculate the inlet velocity. So that means this V1 inlet velocity and the exit temperature T2. So this is actually we need to calculate the T2 and the V1. So here initially what we do, we'll write down some assumptions. So for each and every problem, every time we will write down some assumptions. So the first assumptions for this problem, we will say this is a steady flow process. So a steady flow process, you know the definition of the steady flow process. So that means it will not change with time, right? So as it is the steady flow process, so we can say that the mass, the entering into this control volume and in the it's just going out to the control volume. That means the mass change, if it is steady, the mass change inside the control volume, it will be constant. That means 0. So we can say the mass change delta M CV, that means inside the control volume, it is 0. Similarly, the energy, the net energy change inside the control volume, it is 0. So this is the first assumptions, and we will say that there will be no work interactions. No work interaction. And other word we can, so let's say this is two assumptions we have. So if we start with the analysis, guys, when we will analyze this problem, at first we need to calculate the velocity V1 at the inlet of this nozzle here. So as we said, this nozzle, we consider this is the system. We take this system, we put this dotted line, so that means it is the control volume, and mass, actually it is crossing the boundary during the process. So mass, this is the this control volume boundary, that means control surface. So mass is crossing the boundary, you can see this way. So what we can say, as we have only one inlet and only one outlet, so mass at this inlet, let's say M1, the mass flow rate, and mass flow at the outlet, let's say it is M2 dot. So if it is the steady flow process, so that means the net change of the mass inside the control volume is 0. So that means the amount of mass is entering into this system is equal to the amount of the mass exiting through the system, through the outlet. So that means what we can say, this M1 and M2, they are equal because this is the steady flow process and they are equal. So we can, to avoid any complexity, we can say it is M on M2, it is equal M. So this is actually the mass. Okay, so now if we start the first part of this problem, so let's go to the Next slide. So the first part of this problem, we need to calculate the velocity, right? So as we know, the mass is given 5 kg per second. So we know the formula, the mass flow, it is equal rho1 v1 a1, right? Yes. So here we know the area a1, we know the, you know, the okay, so we need v1, so we will calculate this v1. This is unknown, and we know the mass. So the mass is known, the velocity is unknown, that we are going to calculate. Area is known, but we don't know the density. But what we know, guys, it relations between density and the specific volume. So rho equal 1 over small v. This small v, it is actually the specific volume. So here, as it is for the inlet, so we can define it like this: rho1, it is equal 1 over v1. So this relation, it will be kind of like this: m equal 1 over small v1 capital V A, right? So we know actually this mass, we know this area, we need to calculate this, but what we don't know this specific volume. So we will calculate the specific volume for these given conditions. So for, you know, pressure 1.8 MPa and the temperature T1 equal 400 degrees centigrade, you see 400 and 1.8. So for these conditions, from table A6, so from table A6 we can write the specific volume V1, it is 0.16849 meter cube per kg, and the Hayes one, the enthalpy is 3251.6 kilojoule per kg. So we know this from the table. I'm not showing you the table again because I don't want to increase the length of the video. So it is from table A1 for this pressure and this temperature. So now you see, guys, here we know this V1, here we know the area, we know the M. So if we substitute all of these values, then we'll get V1. So do that. So now substitute all these values. So let's say it will be M equal 1 over V1 A1, or you can say M equal 5, it is kg per second. 1 over V1 is 0.16849 meter cube per kg. Velocity V1 we need to calculate, and the area is 0.02 meter square, right? So what I can do, guys, here is this meter square and this meter cube will cancel out, so it will be M, and we can cancel out this kg. So if we simplify this, V1 it will be equal 42.1, and we have this meter and this second, so it will be meter per second, the velocity. So this is actually the first section, the first part of this problem, that how we will calculate the velocity at the inlet of this nozzle here. So we got the velocity V1, it is unknown. So now what we need to do, guys, we need to calculate the temperature, the exit temperature T2. What will be the exit temperature, right? So now what we need to do, we need to do some energy balance. So from the observations we have, we said, and the assumption, we said it is a steady state flow. So for a steady state flow, we know the energy balance is E in, the energy out, so it should be dot, it is dE, the system, over dt. So as it is the steady problem, so that means this delta E, it is 0, so this term it is actually 0, so, which means the energy in, it will be equal to the energy out, right? Yes. So we know, I already discussed the formula earlier. So here actually we have, so what will be the energy here for this inlet? You can, guys, remember when I showed the the theories, then I already discussed the energy balance, right? So when I discussed the energy balance, you see we had three different energy. It was the heat, work, and the mass. Right? We had the heat energy, the work energy, and the mass energy. So for this inlet, do we have any heat energy? No. Do we have any work energy? No. But we have the mass energy and we have the velocity. So if I write down that equation just for you, so I don't want to write it down again. So let me write the final term for the inlet. So it will be, the M, the mass, and the haze plus what it is, the V square over 2, right? This is we can write from here. If you see that energy balance equation, we had Gz, but we have no elevation here, so that term will be 0. So what we can write here, as it is for inlet, if we say this is process 1, this is process 2, we can write haze on V1 square. And we already know M1, M2, this is equal M. So we can write it as M. So the right hand side, here it will be the same. M haze 2 V2 square over 2. What else? What else is happening, guys, here? You can see we have another thing. The heat transfer is happening. This Q out 2.8 kilojoule. So that means we have another one, the Q out. So that will be the the energy balance here. So we are not going to consider all other the energy in, because no energy is in here, or no work interactions. So that both term, the Q in and Q out, it will be 0. Sorry, Q in and work in is 0, but Q out it is not 0 because we have some heat transfer. So Q out it is not 0, so we need to include that on here. So we'll discuss during the lecture in details this formula. So this Q out at this rate of change, we know the formula, here it is given the heat transfer to the out. So Q out, how we will get if we divide the mass flow rate by using the so if we calculate, if we want to calculate Q out, then we need to do this. We need to just divide the mass flow rate from this the rate of change of heat transfer. So Q dot over M dot. So this is actually the formula. So what we can do, guys, we can write this Q dot over M dot, this Q, it is let me just put it like this for now. So as we have M dot here in the both left and right hand side, but only for the first up, but not with this one. So what we can do, we can divide M dot in both side, like M dot here, we can just divide M dot in the both left and right hand side. So then we can eliminate this, and then it will be Q out over M. So this is actually this small Q out. So what we can write here is haze on V on square over 2, it should be V on square over 2 equal haze 2 V2 square over 2, and this is Q out. So what we can do, guys, here, we know everything. Look, we know haze on, previously I calculated from the table. We know V1, we know V2, we know Q out. So if we substitute all these values, then we'll get haze 2, the enthalpy at the the exit. So let's put all the values here. Haze 1, we know it is 3251.6 plus V1. What is the V1? We get it is okay, we got okay, I think I need to write it down again. So it will be haze 1 plus V1 square over 2, it is equal haze 2 plus V2 square over 2 plus Q out. Okay, so the haze 1, we got haze 1 equal 3251.6, V1 equal 42.1, it is a square over 2 equal haze 2. We need to calculate. V2 is given from the problem, you can see V2 is given 275. So this is a square over 2, and the Q out, it is 2.8. So if we substitute, if we solve this, then we'll get haze 2 equal 3211.9 kilojoule per kg. Okay, So we got this. So now we have H2 and we need to calculate. So now we need H2, we need to calculate T2. So from the table A6, from table A6, we earlier calculated the specific volume and the enthalpy H1. So if we know any two properties, then we can find out the other one. So here, as if we know the pressure and if we know the enthalpy, then by using this pressure and enthalpy we can calculate T2. So from the table, so we need to calculate what will be the temperature for this enthalpy. So let's say it is kind of like this, 32119, and we need to know the temperature T. So we are going to do some interpolation from the table. I'm not showing the table because you already know how to use the table, right? So from the table, what I found, for 350 degrees centigrade temperature, the enthalpy is 3150.1, and for 400 degrees centigrade temperature, the enthalpy is 3258.1. You see that we got from table A6. So here, what we found, the temperature, the enthalpy is 321.9. It is in between this 3.10 and 3258, and the temperature is here 350, it is 400. So we will get a value in between these two, 350 and 400. So you know how to do the interpolations. So the interpolation, I think you all know, but still I'm just writing here. If you want to do the interpolation, this very simple formula, we'll write this one at first, minus this term over this term minus this term. Let's see. Let me write it down. It is 3211.9 minus 3150.1 over 3258.1 minus 3150.1 equals. So you see what I did in the left hand side, it will be the same at the right hand side. So that means T minus 350. T minus 350 over 400 minus 350. 400 minus 350. So that's the same thing. What we did in the left hand side, you will do the same thing in the right hand side. And if we solve it, then the temperature, it will be 378.6 degrees centigrade. So what we got, guys, this is actually the exit temperature. It was, we need some time, but it is not a complex problem. It is very easy problem. Here what we did, we just used this energy balance equation. We calculated the enthalpy. So when we know the enthalpy, when we know the pressure, we use that two properties, and from table A6 we did some interpolation and we got the final temperature. So that's it. So here the most important part was here how you will do the the energy balance. So for energy balance, you can see we have no the energy in, no work in, so this two term will be 0. So we have only this term, the mass. I showed you earlier, so during the lecture I will discuss it a bit more. So I think that's it.